So how many here know how to read music notation? Actually, wow, that's quite a bit more than I was expecting. I'm going to talk today about optical music recognition, and first a little bit about myself. I'm a PhD student in the same lab as Alistair in the Distributed Digital Music Archives and Libraries lab. We're part of McGill's School of Music. Yes, we have technology in a school of music, and I think that's kind of cool. What do? We do digital libraries for music, and that can be audio or it can be symbolic, so music notation. Just in case, just so we're all clear, optical music recognition is optical character recognition for music notation. Just so that's out of the way, because people say optical music recognition, is that like, you see a picture of music and you try to guess the artist or something? No, that's not what it is. And why are we doing this? Well, what we're trying to do is we're trying to build a Google Books for music notation. Google is digitizing millions and millions of books, doing optical character recognition on it. You can search it, you can find books, you can find text. That's all great. What we're trying to do is we're trying to build the technology to do the same thing for music notation. Why do we want to do that? Well, we want to do that so you can search it, so people can analyze it, so they can find patterns in it, and so that we can expose huge, vast libraries of music notation to the world. So this is sort of the grand idea behind it. So some people think that our task is to tell a computer how to understand music notation. And that seems like a very simple thing to do until you think about it. So instead, our task is to teach a computer how to understand music notation. That's a bit trickier. And I'll run through some of the tools that we're using to do that. But first, let's look at some music. Why is music hard to teach, hard to get a computer to recognize? Well, first of all, unlike text, you have two dimensions, where you'll have pitch on the vertical and time on the horizontal. You'll have a whole bunch of different things happening at the same time. So you have chords here. These are all different notes. You have things simultaneously happening up here and down here. And you have all sorts of different things around that tell you how to interpret that music notation. So it's quite a bit trickier than just sort of seeing a C on the, I guess it would be that way for you guys, seeing a C on a page and transcribing that as a letter C. So things like clefts. These are clefts, if you don't know. These tell you which line a certain note is. So this would be a B flat, because you have key signatures, and it just goes on from there. You have durations, so one note is longer than another or shorter than another. Articulations, to if you want to accent a note, so you want to put an emphasis on a note. And there's a whole bunch of implicit knowledge in this, where things like this symbol here tells you to repeat. So you'll get through and then you'll come back and you'll repeat this passage again. So there's a bunch of knowledge in here that a computer finds really, really hard to figure out. And my favorite example is this note, this kind of note. So one of the things that this kind of note represents is that if you have a dot on the top of the note, it actually means play the note very, very shortly. So it's called a staccato. If, however, you move the note around to the side, it means play this note 50% longer than you would normally. So you have a positioning of symbols that actually mean things to a computer. So that's a bit of why music notation is kind of hard. What we do specifically is we work with older notation. So not all music notation looks like the sample that I showed you. Some music notation looks like this. And this is a style of music notation called Noom notation. mostly used by the church, and mostly from about 1100 to about 1600 CE. So there's a lot of this notation in libraries and archives around the world. A lot of historical and artistic content is bound up in these books. And we want to make this available. We want to teach a computer how to do it. So how do we do it? Well, our main tool for doing this is Gamera. It's a Python and C++ framework for document and image analysis and shape recognition. And I want to point this out for any of you who are saying, oh, well, this is just for music. It doesn't really interest me. It's not just for music. It's for any type of document images. You can use it, people use it for barcode recognition, for optical character recognition, for a whole bunch of different things as well. So, if you're doing optical music recognition, there are some general tasks, and I'm gonna give you a demo, but just as a high level, what we have here is we start with binarization. Usually we get a color image, and we need to turn it into black and white. It makes things a lot easier to process. One thing we have to do, the next thing we have to do is we have staff removal. Those are the lines that go across the page that connect everything and tell you where the pitches are. Well, because we're doing what's called connected component analysis, where we look for shapes based on the pixels that are connected together as black pixels, we have to remove any lines that connect things. So we have to do some analysis there. We have to do shape identification. So we have to figure out, we have to teach a computer what a shape means. We have to say, this is what this shape means versus this is what this shape means. We have to go back through and correct. We have to find any errors that the computer made and fix it. And then we have to export it into some sort of symbolic music notation encoding. So basically turning an image into something that a computer can edit and read and manipulate. Remember, this is important, there is no such thing as plain text for music. There's no sort of base music encoding system. We need some sort of structural encoding system in order to represent music notation to a computer. So now I think I'll give you a little demo. If we can get IPython up and running. And so what I was going to show you first is just make sure we're in the right directory. No, we need to go to the desktop and Montreal-Python. Okay. And we're just going to import some image analysis system. And import image ops and import image enhance. And we're going to open this image. So we have an image here. This is what it looks like. Oops. You can't see that. This is what it looks like. So it's a page from a book that we're working on. This is the Noom notation. And we're going to try to get the computer to figure out just where the notes are here. So we have image. I'm going to open that image. So the first thing we're going to do is we're going to just pull out the notes. And one of the nice things about that image is that the staff lines, the lines connecting everything together, are in red, and the notes are in black. So we're going to just separate out the color layers. So we have to do image ops. Just do that, and then we have a red layer. And notes dot save. Oops. Oh, notes equals that. So basically, what we're going to do is do a threshold that we're only going to get red values between these values. We're going to open that up, and we're going to save that. Oh, where am I here? And from that image that I just showed you, we end up with an image like this. So you can see all the points have been removed. All the lines across have been removed, and what we're left with is just the text and the shapes. So now I'm going to load up Gamera. And Gamera is actually fairly simple. It looks like this. It's actually a Python shell, so you can do all of the things that you're familiar with. But what it also has is it has a number of tools for working with images. So if I open that image that we just created, give it a second here, and we'll open the only red image and save it. So we have an object here, and you can see all of the different types of analysis we can do with it. So we can do some color processing, deformations, displaying, do some edge detection, and things like that. You can see that okay. But what we specifically want to do is we want to make sure that we can pull those shapes out that we got from the image process. So Gamera has what's called an interactive classifier, and what it is it's basically any machine learning people in the room. Anybody machine learning? 1, 2 sheepish people. So basically all we're doing is we're trying to figure out shapes. We're trying to get a computer to automatically tell us this shape is this. And how we do that is we're going to load in a library of these shapes. So it's a pre-constructed library. It's going to be something that we've been working on, and so you can see here that these are clefts. These are types of clefts. These are different shapes here as well, and then we're going to load in the image that we just created here. Oh, well, okay, just give me a second. I had a backup image just in case this happened. Sometimes colors get inverted. So I've got the same image here. There we go. So it's the image that we had before. And you'll notice here when it's opened it's actually pulled out all of the shapes on this page. Let me make this a bit bigger. So you can go through and see all of the connected components. So these are all of the things that it's found that are actually connected together on the page. And they're white, which means the computer doesn't know about it. It just says they're a bunch of black pixels. Normally what we would do if we had time is we would clean up all of this stuff so that we only get the things that we want to recognize. But I'm going to load in a set of pre-cleaned symbols so that we get rid of all of the things that we don't want. And then it's as simple as we have you can't see this, but there's a menu option that says group and guess all. And so what it will do is it will, based on the contents of the classifier that we've loaded in, we'll try to guess what each one of these shapes is. So group and guess all, and we set some parameters. So do that, and it thinks for a second, and what it's come up with is it's actually found some shapes. So this shape is called a Clefts. This shape, there are a bunch of other shapes that it's found. So what we've found is we've actually detected we've detected shapes, and you can imagine this working for any sort of classification system, where you have some image shapes that you want to figure out what they are, and you can do that as well. The nice thing about Gamera is that while it's an interface, it's also a Python library. So you can write all of this. Anything that's exposed in the interface is also exposed as a library function call. So you can do all of this. I didn't do it for time, but you can do all of this classification programmatically as well. So you can build things like web apps that will do this sort of thing as well. So that's a bit of my demo. So what we end up with is we end up with something like this, where we can actually tell what the pitches are, where the pitches are, and what the shapes are, so that we can figure out how to represent this in music. So we can then write this out as a music representation into something that will actually understand music notation. You can edit it. We specifically work on searching it, so you can actually look through and find pitch sequences and notation sequences. So just to recap, we can clean up images. We do binarization. We remove the staff lines, do connected component analysis, classify. We need to recombine with the staff lines in order to find the pitches again. And then we save the image and the musical data to some sort of representation format. And we're part of this music encoding initiative schema. And that's me. Our lab releases our code at github.com/ddmal. We've got some really cool projects on there, and if if you have internet, you can look them up and ask me. I've got a couple other of my lab members around here, so you can, if I don't know anything about the project, I can certainly point you in the right direction, and I have my own GitHub as well. So thank you very much. Questions?
I have a question.
Yes.
How much stuff do you actually have? Like, what's your tool? How many manuscripts you have? How do you scan them? What's the physical side of the process? I'm very, very curious.
The physical size of the process?
What's the physical side, I would say? Meaning, well, first of all, how many what's the volume of video information you deal with, and how you scan it? This is pretty old stuff.
Yeah. This summer we just did a fairly large scale one book that was 2,340 pages, and we're now working on another book that's about 500 pages. Our idea is that we're actually building the tools so that libraries and archives around the world can actually do this themselves and then contribute it back, so that we're sort of building this collaborative music search system. So theoretically, to answer your question, the scale is global. That's how big we want to make it.
And what's the sorry, I'll wait.
Okay.
Sure, just a quick, simple question. When you, the output format that you use, the XML format,
Mm-hmm.
is it easy to take that and put it into something like MIDI or something that can be played?
Yes and no. I mean, MEI, Music Encoding Initiative, is a fairly new format. We're working on tools that can transform it. There is no reason why it can't be. We just need to make it do that. I've had a bit of a go at it, but yeah. But that's ideally what it would do. We'd put it into a score editor, put it into MIDI, put it into any search system, things like that.
So the other question was, I want to ask was, how much manual intervention do you need to do on this?
Less and less. The idea, the theory that we work on is that as we start a book, we start from scratch. We train it on a few symbols, and the computer gets better as it sees more symbols. And so as the computer gets better, the manual intervention gets less. And there's a peak. We get about, for some types of music notation, we get about 98% accuracy, which is still fairly low, but but it's better than having to hand transcribe it. Yeah.
Yeah, but so how do you verify it? Like,
Humans. Like we have people who sit there and do that.
basically, answers from there.
Yeah, they basically correct it.
It'd be nice to just hear it. Really cool process.
Yeah. Okay, I think I'm out of time.
Thanks.
Thank you.